Hi everyone, I'm Yifan Cai. Today I'm going to present our work, VeriDB, an SGX-based verifiable database. This is a collaborative work among Alibaba Group, Georgetown University, the University of Pennsylvania, and the University of Utah, with Wen Chaozhou, Yan Qingpeng, Shen Wang, Ke Ma, and Feifei Li. First, I'm going to show the motivation of our work. For traditional cloud storage or cloud computing services, a user would choose a service provider that should trust and store her data on it. When the user needs to do some analysis on the data, she generates a query to the cloud and gets the results returned from the cloud. Everything here is based on the fact that she trusts the cloud. However, for some sensitive data, the trust here is not enough. The user may want the cloud to provide some extra evidence to show that the results are correct. Or when some unexpected things happened, such as the data was tampered with by some employees or external attackers, the user may want the cloud to detect them and alarm her. Let's look at a concrete example. The user has a table salary stored on the cloud. The user asks the cloud, what is her salary in March? Though the value is actually 7,000, the cloud may modify the value to be 4,000 and tell her that it is 4,000. Another scenario is that the cloud may even return falsified results without tampering with the data. Here, the user has a table inventory stored on the cloud with the name of some fruits and their price. The user asks what kind of the fruits are worth more than $1.6. The answer should be the apple and the peach, while the cloud can deliberately give some incorrect results. Now we give a high-level description on the scenario of the problem and our goals. We focus on the cloud client model, where the client does not trust the cloud. We do not consider the multi-party client scenario because consensus is not our main focus. We also take advantage of the existence of SGX, which provides an environment that data inside cannot be tampered with. We assume that the cloud is Byzantine, which means the cloud has full control of the database except for the data inside SGX. In this case, the cloud may add, change, and delete any data. As for our goals, we want the system to stay quiet when everything is fine, but it should be able to detect malicious behaviors and alarm the user. We also want the system to support general SQL queries and has low performance overhead. There are some strawman solutions that can somehow provide correct results but have significant performance overhead. One way is to use Merkle hash tree to verify the integrity of data. As is shown in the figure on the right, Merkle hash tree uses recursive hashes to ensure the integrity of data. However, the root hash may become a bottleneck of concurrency. Another way is to store all the data in trusted memory. However, trusted memory is currently a scarce resource, which is typically around 100 megabytes. If the trusted memory is not enough to store all the data, then swapping between trusted and untrusted memory takes place, which introduces significant performance slowdown. We showed that the strawman solutions are not enough, and we made the following contributions in VeriDB. First, VeriDB uses verifiable storage and verifiable execution, and combine them to achieve verifiable results. Second, VeriDB supports verifiable relational tables and general SQL queries, not only the key value stores. Last but not least, VeriDB has reasonable performance overhead. Next, we are going to look at the design and some technical details of VeriDB. We first show the architecture of VeriDB and the reasons why we have such designs. Firstly, we argue that the data must be stored in untrusted memory. As trusted memory is around 100 megabytes, storing all the data in it is not a very good choice. Secondly, in order to ensure the integrity of data, we need to maintain some read-write primitives in trusted memory. These primitives are small enough, they are usually kilobytes or megabytes, and will help the verifier to check the integrity of data. We will discuss how the primitives work in the next few slides. After we have a verifiable storage layer, we need to have an interface between the query executor and the storage to ensure that based on the correct data, the system can actually return correct results. We also need a query portal in SGX to connect to the client via a secure channel. The query portal would ensure that the system actually executes the query that the client sends. And the query compiler will correctly compile the query from the client and send it to the executor. The entire workflow will be as follows. The client sends a query to the query portal. The compiler correctly compiles the query. Next, the executor would fetch data from the read-write primitives, which are responsible for verifying the data, and send it to the executor. Finally, the executor finishes the query and sends the results back to the client. After having a high-level idea of the system, we are now going to dive into some technical details of VeriDB. One of the most important things is to make the storage verifiable. The basic idea is to take advantage of the read-write consistent memory, which was proposed by Blum in 1991. The goal of read-write consistent memory is to make sure that whenever there is a read operation, it should get the contents modified by the latest write operation. To achieve this, we maintain a read set and a write set. Whenever there is a memory operation such as get, insert, update, delete, we update the sets correspondingly. If the data is not tampered with, we will find that the two sets are consistent. Concretely, we construct a hash of tuple which includes the information of address, contents, and timestamp on each operation. To save the space of reset and the write set, we update the sets by computing the XOR of the hashes. The Conserva paper introduces a more efficient parallelizable approach to compute the set hash. Let's look at an example. At the beginning, there's no data in the table, and both sets are also empty. The first operation is an insertion. Here, data 1 is inserted, and we add a tuple address data1 t1 to the write set. Next, there is an update operation on t2. We first check whether the data is still data1, add it to the read set, and then add the updated data, which is data2, to the write set. When there is a read operation on t3, we also check whether the data is still data2 and add it to the read set. To keep the two sets consistent, we need to perform a virtual write operation and update the write set. Periodically, the verifier would wake up and check that all the reads are consistent with the latest write. It reads all the data and adds it to the read set. If the verifier finds two sets are consistent, it stays quiet. Otherwise, it raises an alarm. This is the overview of the technique. In our paper, we have a more detailed description on what to do for each operator and how to avoid stopping the entire system during the verification. Now we have verifiable storage, but it is still not enough for providing correct results. We still need some way to prove the existence or absence of data. To solve this, we add an extra field next key to the table. For each table, we add a row to the beginning whose key is negative infinity and we store the value of next key for each row to make it a key chain. In this way, we can prove the existence or absence of a given key. For example, the executor may want to look for some data whose key is larger than ID2 and smaller than ID3. When it finds such a row with key ID2 and next key being ID3, it knows that the data it wants does not exist. This technique also gives a solution to range queries. To make sure that range query is correct, we need to check three principles. The first one is that we do not miss anything in the beginning. To achieve this, we will find the first row whose the next key field is larger or equal to the start key, and start our scanning from the next row. The second principle is that we actually reach the last row, so we do not miss anything in the end. We will check the next key field of the last row should be larger than the end key. Finally, we need to guarantee that all rows are chained, so that all data is collected in the middle. This is guaranteed if and only if for all rows, the key is equal to the next key of the previous row. We will explain this by an example. Select star from data where key is larger or equal to ID1 and key is less or equal to ID3. By the first principle, we'll start from the first row. We continue scanning until we find the next key, ID4, which is larger than the end key, ID3, in the fourth row, so we finish the scanning. Besides, we find that all the keys are changed. Therefore, all three principles are followed. With the combination of verifiable storage and verifiable data access, the executor is then able to provide correct results. Now we are going to look at an end-to-end example for the query execution. We have a query on the upper right corner. The query executor first looks into the orders table, gets the negative infinity, and starts from the ID1. This step is to make sure that ID1 is exactly the first row and no rows are missing. It then looks into the inventory table and finds a row with ID1. It compares the count and generates the result tuple. Next, the scan cursor is at the row with ID2. The executor checks the next ID of the previous row is exactly ID2, so the data is chained. It then looks into the inventory table and finds a row with ID1 in the ID column and ID3 in the next ID column. Therefore, it can guarantee that ID2 does not exist in the inventory table. Finally, the executor tries to find the next tuple in the orders table. It reaches the infinity. Therefore, it will make sure that there is no more data in the orders table and all the execution has finished. In addition to providing correct results, we also design and implement some optimizations to improve the performance of the system. As mentioned before, we used reset and write set to guarantee the integrity of data. When there's multiple threads performing memory operations, to avoid data races, we need locks for the sets, and they can easily become the concurrency bottleneck. To avoid this, we separate the reset and the write set into multiple subsets, and we use a mapping function between the sets and the addresses. In this example, we assume that address 1 and address 3 will go to the first subset, and address 2 will go to the second. Therefore, memory operations on address 1 and address 2 can execute concurrently, as is shown in the animation. We also have some memory operations on address 3. When the verifier wakes up and starts the verification, it would collect all the tuples from all the subsets and check whether the read set and the write set are consistent. Due to the limit of time, we only discuss one of the optimizations here, and if you are interested, you can read our paper for the rest. Finally, I'm going to show some evaluations on the performance of VeriDB. First, I would present the results of reset and write set updates. The rightmost 4 bars are the baseline, which do not involve updates of resets and write sets. The middle bars are the results where we introduce resets and write sets. Each update would introduce 1.5 to 2.2 microseconds of performance overhead. We also find that hash operations make up most of the extra overhead. Here, insert and delete operations need updates to the next key fields. Therefore, they take longer time than read and update. We also evaluate the performance when we start the verification process periodically, as is shown in the leftmost bars. We find that the verification process only introduces small overhead. We then compare the performance of VeriDB and MB-tree-based solutions. Because MB-tree involves more hash calculations, it is much slower than VeriDB. Besides, the root hash of MB-tree may become the bottleneck of concurrency, which will further slow down the whole system. We also perform evaluations on macro benchmarks. We select query 1, query 6, and query 19 as examples. Query 1 and 6 involve scan, filter, and aggregate operations, while we let query 19 execute a nested loop join, which takes longer time. We can see from the figure that most of the performance overhead comes from the scan operators, which is about 2 times slowdown. For other operators, VeriDB does not lead to much performance slowdown. Overall, VeriDB introduces 9% to 39% of performance slowdown. Specifically, for I/O-intensive operations, the relatively slowdown will be higher, while the relative slowdown will be milder for computation-intensive workloads. We also evaluate other macro benchmarks, such as TPCC. The results are in our paper. There are also some existing systems that have a subset of the properties that VeriDB has. Concerto has a relatively low performance overhead, but it only supports key-value stores. VirtualDB and EnclaveDB have high performance overhead. EnclaveDB assumes that in the future, trusted memory will no longer be a scarce resource, so it stores all the data in SGX. This architecture does not work well with the current hardware. VirtualDB uses a Merkle hash tree-based solution, so its performance is not as good as VeriDB. FalconDB mainly focuses on the scenario of multi-client scenario. It uses blockchain to do the consensus. However, the performance of blockchain is not so good, and it is not a necessity for the cloud user scenarios. To conclude, in our paper, we design and implement VeriDB, an SGX-based verifiable database that supports relational tables and general SQL queries. To make sure that the system can detect malicious behaviors, we reduce the problem of providing verified results to ensuring verifiable storage and verifiable access. As long as the storage and data access are verifiable, the executor will be able to provide correct results. VeriDB also introduces reasonable performance overhead. It introduces no more than 2.2 microseconds of read and write operators and no more than 39% for analytical workloads. This is the end of my presentation. Thanks very much for listening.